Good afternoon. It's post-Christmas, but I'm still on day 24 of Advent of Code. My name is Kent Quirk. I am a software developer, game developer, and I have been working my way through Advent of Code for 2020. I'm now up to day 24 out of 25. And today is maybe a little bit fun. So we are going to take a look at what the problem is and why game development matters for this one. So here we go. So our premise is that we're done floating in a raft, and now we're on. We've gotten to the lobby, but we have to renovate the floor, and they're using hexagonal tiles, and they're flipping hexagonal tiles on a hexagonal grid layout. So if you've played, there's a lot of board games, particularly any kind of war battle style games or like Settlers of Catan, whatever. They use hexagonal grids. Gives you a little more interesting layouts than just rectangles, more options for attacks and things like that go along diagonals, because you now have three directions that you can work with instead of two on a board. Now, technically, though, it's an interesting problem because laying out that board in memory is a challenge, and it depends a lot on what you're trying to do. So if you're going to implement a game that uses a hex board in code, you have to think about, well, okay, so I have these hexes, and if you imagine laying hexes out edge to edge, they fill the space completely. Hexagons are a space filling grid, but the edges aren't rectangular, and you have awkward square roots 3 in the calculations when you're trying to calculate diagonals and layouts and all that stuff. So there's a couple of different ways of thinking about hexes when you're trying to lay out a game for it. Now, somebody a few years back wrote a really great web page on dealing with hexagonal grids, and I've used it in the past, and I'm going to show it to you now. It's called redblobgames.com. Was written in 2013, updated in 2015. Been updated a few times. It's great because it explains hex grids, it explains how you have to think about them, and it particularly explains coordinate systems. So one way to do it is to do these offsets coordinate things where you take every other row and you offset it, and you can do this, and that's okay, that works pretty well. But the other way that I particularly like is what we call cube coordinates, where if you've ever looked at a cube from the corner, from a diagonal, you realize that the edges of that cube appear to be a hexagon. So if you were to slice that cube perpendicularly, you get to see the layout of hexagons. So watch this. This little picture here is cool. They throw away the things, and you get the hexagonal grid, which coincidentally is the board for Qbert. If you notice that when they put it back together, you get that sort of hexagonal pyramid. Now, since a hexagonal grid has essentially three diagonals, I'll call them, you've got, or three perpendicular axes here. So you have, in this case, they draw the x-axis horizontally, and the y-axis diagonally this way, and the z-axis diagonally this way. Oops, sorry, they call this x, and this z, and this y. Okay, this is one place where I would differ here. Most of the time in game development, when we color axes, we color them x is red, y is green, z is blue, RGB. And so when you look at something like Unity or other game programming platforms, very often they'll show you a three-way axis, and you can tell by color which axis you're looking at, even if you don't see X, Y, and Z. In this case, they have colored X red. No, they've colored, X green, Y red, and Z blue. So they swap the red and the green. But it doesn't matter. It's fine. So the thing that's interesting here when you look at grid coordinates is that if you look at x, y, z at 0, 0, 0, you can calculate an offset for what you have to add to x, y, and z to move in each direction. And an interesting mathematical artifact of thinking about it this way is that moving along an axis is always adding 1 to one coordinate and 0 to and minus 1 to another coordinate and 0 to the last coordinate. So the sum of x, y, and z on this grid is always, for every cell in the grid, the sum of x, y, and z is always 0. That's a useful property in some cases. And my dog is, as usual, upset about something. So what we're going to do is we're going to represent here our grid coordinates, because the main thing we have to do in this problem, I'm going to go back to the problem for a minute. The main thing we have to do in the problem is take some strings that are representative of motion on the grid. So we start at the origin and then we move northwest, south, or southeast. We move around in the grid according to coordinates, and then when we get to the end of our instructions, we flip that grid square from white to black or black to white, whatever side is up. So the data representation I'm going to use here is to do I'm going to give each grid square a coordinate. We're going to walk through our instructions of how to move, and then we are going to add the coordinates that are black to a map by coordinate. And when we flip a black tile to white, we're going to delete it from the map. So basically, in the end, what's going to be in the map are all the black tiles. So we're going to start with an empty map. We'll add to it when we flip a grid coordinate to it, and we'll take away when we don't. So that's my basic structure. I'm using x, y, and z for coordinates, and then we will do a hash of x, y, and z, or not really a hash. We're going to just do some coordinate shifting to get to storing the coordinate value in the map. So let's start. All right, so that's problem number 1. How do we represent a hex grid in our content? And actually, I'm going to, just in case anybody cares, I'm going to take and paste into the chat room the URL of that hexagonal grid discussion, and it's great stuff. Anyway, let's go back to the problem and let's start solving the problem. So first thing we have to do is we have an example here, which is we have a semi-interesting parsing problem, and you may not be surprised to find that I feel like the best and easiest way to parse this is with a regular expression. But first, let's take our inputs, copy them, paste them into the right files, save that, save the sample. We're going to go to main.go, and we're reading input sample.txt, and we are parsing that, and then splitting it up. So I can get rid of that. And now, so the direction, what they've done here with these files is they have just lumped the directions together. So we have to decide, we have to look at southeast is a valid direction, northwest is a valid direction, so are east and west. But if we see an N, we know it has to be followed by either a W or an E, so we can group those things together. So the easiest way to parse this, let's do So we have a bunch of we have a bunch of lines in the array, and so func sorry about that. Okay, so we're just going to walk this array and parse it directly rather than writing a separate parser because it's pretty straightforward. So for underscore line in range lines, then we are going to we're going to write a pattern. We're going to write a regex pattern for all the possible directions, and the possible directions, pat is regex dot must compile, and the pattern we're going to use is either northeast or southeast or northwest or southwest or east or west. Now, I did it very specifically in that order because Go and I think pretty much all the regular expression parsers specifically say that when you have an or expression, it prefers an earlier match than to a later one. So obviously, we want to match northeast and southeast before east, and we want to match northwest and southwest before west. So we're putting east and west at the end of the expression. If we put it first, we would probably screw things up when we had a couple of W's. I don't know, actually might not. I'm not even sure. But, so what we're going to do is we're going to say pat dot find all string submatch within line. And what that's going to give us is an array of string. Because, wait, hold on, find string submatch I think is what we want. Find string submatch just gives us an array of string. Yeah, so it's going to give us an array of all of this match strings in the expression. Which is what we want here. We basically want to take this line that looks like, you know, this. Looks like that. And we're going to split that into a bunch of groups, and it's going to give us southeast, southeast, northwest, northeast, 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 west, southeast, east. You know, so essentially the things we're doing when we have this, we say start at the origin and add all of these operations to it, and then whatever you have, wherever you are at the end, flip that tile. So now we're going to start setting up our grid. So the first thing we do is we need a type tile hex tile, which is a struct with x int y int z int and right now I'm not going to put state in there because we're going to use the presence or absence of a tile in our map as the structure. Sorry, as the indication of whether the tile is white or black. So we have hex tile. Now we need a func which will accept a hex tile and as a receiver and calculate I'm going to call it hash, although we're not actually going to do a hash here. I'm going to assume Oh no, our tiles could go negative. I was gonna say I could assume that the tile would. Ooh, yeah. Here's what we could do. I'm gonna cheat like hell here. We're gonna call all of these an int 16, so they're all 16-bit integers as our coordinates, and we are going to our hash is going to calculate an int 64 from our int 16s by shifting and adding. So we're just going to, that way, so what I'm saying is that the tile value, the tile position will never be more than 32,000 32,000 units in any organization, because it's 2 to the 15th and then a sign. So from the origin, the maximum value will be 32767 and the minimum value will be negative 32768. And that's as far as our coordinates can go. None of these strings are long enough to take us that far out, so I'm not worried about it. We'll just have to see where we go from there. I mean, if they were to blow it up somehow, then we can deal with this. But for now, this will work. And so for my hash, I can get a unique value from the coordinates simply by taking the x, y, and z value and shifting the x 32 bits, shifting the y 16 bits, and leaving the z alone. So that's exactly what I'm going to do here. I'm going to return. So we're going to do an int 64 of x shift left by 32. And then we're going to OR in an int 64 of y shift left by 16 h.x, sorry. This is h.y, and I'm going to OR in an int 64 of z. And whoops. All right, so negative numbers, the representation of negative numbers is what's called 2's complement, which means for negative numbers, all the high bits are 1 rather than 0. So int 64 of -1 is represented in hex as, in 16-bit hex as FFFF. And then when we say int 64 of that, what we're going to get is 16 Fs. And what we actually probably want here is to take that value and convert it to, mask off those high Fs. So that the value that we have doesn't have, we're not messing around with negative numbers here, and we can put them back into negative form. If we ever need to deconstruct this, I'm not even sure we're going to need to deconstruct this. So let's just do this. So we're going to take that in 64. So const mask 16 equals 0x FFF. So that is, in Go, constants have no defined type other than it's a generic integer. And so int 64 of FFF is the same as int 16 as FFF. It doesn't matter. So I can use them without casting them. So, and where are we? Ampersand mask 16. this is h dot z. H dot z. Save it. All right, so so this is how we're going to get the hash that we are using in our map. And so we also need a no, it's not a const. We need, so our moves, when we see northeast, we are going to want to look up what a northeast move is. So that is going to be, if we look at this, this is minus, so what we're saying is northeast is plus 1 x and minus 1 z and 0 y. So what we're going to do is we're going to build a small map, which is our coordinate map, our offset map, which is how we move. So when we move northeast, we can look up that and we can add it to the hex tile. So we're going to have a func that takes a hex tile as a reference, add, takes another one and adds it to the source. And we're just going to say, whoops, and then do the same thing for y and z. There. All right. So x, y, and z. And then we just return. So now we're going to not a func. Let's just declare coords to be a map of string to hex tile, and we're going to define it equals so northeast becomes, a hex tile of, so northeast is x is plus 1, y is 0, because we're moving along the y-axis, and z is minus 1. And again, you could calculate the third one from the first two, because the sum of every coordinate is always 0. So now northwest, x is 0, y is minus 1, and z is plus 1. No, got it backwards. Sorry. Y is plus 1, z is minus 1. That makes more sense. So when we are moving north, z is going in the minus 1 direction. Southeast, southwest. Okay, so southeast is x is 0. Y is -1. And z is +1. Southwest, x is -1. Y is 0. And z is +1. And then finally we have east and west. So east, x, so east and west, y is 0. And for east, x is +1, and z is -1. Wait, no, that's not right. I got reading it backwards. Okay. And with west, z is still 0. I'm going to just rearrange these so they're a little... So east and west are along one axis, and they are both z is 0. Northeast and southwest are along one axis, and they are both y is 0. And northwest and southeast are along one axis, and they're both x is 0. And the signs are opposite for the two sides, and so this looks like it's probably correct. So that's my coordinates. And so now, for, whoops, moves is that find string submatch takes just a string and splits it up and gives you an array of moves, or a slice of moves. So now for underscore move in range moves, we are going to say the floor is a map of the hashes of tiles, so in int64, and we're just going to use an empty struct for now. It may be that in part 2 we're going to have to do some more with the data on the individual tiles on the floor, but for now we're just going to add an item to the floor, and we're going to make this. So so we're going to create current position as a hex tile, and we don't care. Why is it not happy with me? Oh, what's this? There. Okay. We don't care that, I mean, it's going to get initialized to 0, which is what we want. So we have a position. And now, for every move, we're going to say pos dot add coords move, because move is a string. And we're going to look it up in coords, and we're going to add the position to it. And at the end, now we have just moved, and at the end, we say floor pos dot hash equals struct an empty struct. So if it exists, oh, actually, no, what we need to do is we have to say if we found it in the floor, then we need to delete it. So, otherwise, we're going to add it. And D24A is going to return an integer, which is the size of that map. And return length of floor. And that will be the number of black items in the thing. So foo. Oh, not lines of 0, just lines. All right, I see no errors here. Looks like it's good, so we can try running it. Go run main.go. 4. 4 does not sound correct. Oh wait. Is it, are we checking this? So tiles are hexagonal. So the reference tile is the center of the room. Every line starts from the same reference tile. Okay, so that's right. I'm just debugging here a little bit. So this is saying that 10 tiles are flipped once to black, 5 more are flipped twice to black, then back to white. After all those instructions have been followed, a total of 10 tiles are black. Oh, okay. So input.text should be input sample.text should be 20 lines, which it is. Okay, and they're saying that some of these instructions give us the same result. So why is it yelling at me? You know what? I'm going to just change these %s's to %v's because then the right thing happens. It just prints them as best it can. All right, let's try again. So, oh, add is not working. Oh, I'm starting from scratch every time. Pause needs to be outside the loop. It's a 6 R black. And 4 are white. So what did we get wrong here? I'm going to pull all these in and I'm going to sort by position so I can see what I think we saw. Copy. I'm going to do this, paste that in. Sort lines. So, that one's black. Oh, so this, no. So it claims that it flipped, flipped that one 3 times. And it flipped that one 3 times. So it keeps coming up with the same one. So maybe so either I got the coordinate sets wrong, or I got the addition wrong. Let's print out a bunch of garbage here. All right. Let's run this and know that we're going to get a bunch of crap. Wait, why did that? So first of all, this should be \n, but it's only doing one move. for each tile. So did I mess up the find? Oh, it's not find string submatch, it's find all string that I want here. Well, that was silly. Okay. This is now going to print a lot of garbage, but... and find all of them. Now it says 16. Oh, in this, so pause. Now pause comes in here. That's why it was only getting, it seemed like it wasn't moving. I wasn't thinking it through. Okay, so we're going to start here, and now we have a new position, and the answer is 10, which is correct. Wow, that was a little bit more painful than I expected. All right, so now let's do this for input.text. $346. Now, is that a reasonable number? Because how many lines are there in input.text? 408. Okay. Yeah, that seems like a reasonable number. Get rid of this. All right, 346. Submit. That is correct. Okay, now let's take a look at part 2. The tile floor is meant to be living art exhibit. Every day, all the tiles are flipped. Oh god, we're back to a cellular automaton, except that now our automaton is a hex grid rather than a rectangular grid, which is fascinating, kind of cool. So we need to make our grid. We're going to turn back to our example, and we still have our coordinates. Our coordinates make it easy to calculate our neighbors because we just iterate through the coordinates and we say, what is the state of the neighbor? So, cool. That's an easy way to count neighbors. And we just have to basically make a copy of our map on each frame. Excuse me. So, we are going to day 24B has to take the results of day 24A and work with those. We don't need to parse them again. We just need to iterate. So what we're going to do here is day 24A is going to take a line and it is going to return our grid of tiles. So since we're going to want to run a generation on it, I think I'm going to make it into a type. So, so it's going to return, instead of an int, it's going to return make, I'm just going to return this object. Yeah, no, I am going to do that because I'm going to want to check for neighborhood and things like that. So we're going to define a type, floor, and it is going to be that. Func new floor. Yeah, we can do it this way. Let's refactor this. I'm going to take a set of lines of string, and we are going, oh, actually I don't want to delete those. I still want it there. And we're going to parse in new floor. So we're going to parse and populate in this. So D24A is just going to be a trivial call to new floor, basically. So new floor, lines of string, and turn floor. Alright, so D24A should still give me 10. Okay, good. So we refactored that. And now what we can do is we can also add a floor function which says, well, let's write day24b. So now day24b floor colon equals new floor lines and so how many generations? 100 generations. Instead of returning floor, we're just going to return an int again, and let's take the length out of here. So for every floor, we're going to say floor equals generation equals floor dot generation. rename this to parse. Because I'm going to need a new floor. Func. Okay. I didn't call it new floor because I'm not returning a pointer to the floor. I'm returning the floor object itself. That's because I'm going to make new ones and clone the contents essentially by calculating the generation. So the interesting thing here is, oh, Shiner. The interesting thing here is that we have to iterate over black and white tiles, so we sort of need the extents of the floor. So we need to know what is the farthest tile. We need to be able to get the extents of the floor on all axes. So let's do this. Because we need a pair for every value, I'm going to do func. I'm going to do it. We're going to put them in. Basically, the reason for having these extents as separate thing, we need to make 3 nested loops. We have to loop over the extent in the x, y, and z with a buffer on all sides. So we have to go one more than the extent in all directions. And so it's probably just easiest for us to do an x extent, a y extent, and a z extent. And they're basically all the same function with just a different coordinate. And if we really wanted to, like, I personally prefer to use x, y, and z as explicit variables and be able to say .x, .y, .z when I'm looking at coordinates of things. You could certainly make this an array of 3 integers and do everything with indices, or write x, y, and z accessors that access the appropriate index. And then that lets you genericize a couple of functions. And there's nothing wrong with that, but for 3 axes, it doesn't really make that much difference. It's just easier to copy and paste. So that's not go-ish. Extents. Oh, and it takes a receiver of floor, x extents, and it returns an int 16, int 16. And we're going to do the same for y and z, but so we're going to just go for underscore value or tile in range of f so we're going to iterate over by using the range. We can ignore the key because the key is just a hash. We don't care. We just want the values. So we're going to say x min so the minimum value we're going to give a large positive value. I'd like to know what go calls maxint. Wait, that's math.maxint16. And xmax all right, and now we can say if x min is greater than tile.x, x min equals tile.x, and the same thing for x max. And then we are going to end our loop and then return x min minus 1, x max plus 1. Now let's have the true extents, and then we'll modify the extents in our loop. And this has to be returning a pair, so we have to wrap it in parens. And it doesn't like tile. Oh, bummer. I'm storing in my tile, I'm storing an empty struct. What I should really store is the hex itself. That's just a silly idea. So let's just fix that. This here. And then here we are going to store pos. So the value at each tile is the tile itself, and then we just delete it if we don't need it anymore. So now we can look at that tile and we'll be fine, and we return this. And so now I'm going to just copy this and make it y extents yeah, I'm still going to do it this way. It's making me feel a little bad to do it this way, but I'm going to do it anyway because I just think it's harder to. So now so we're going to change all of those to y. And then we are going to go to the one following this one. Oh, and it got collapsed. Oh well, nice try. So, just to save ourselves a little bit of grief, do this again. And so now we take the y's and change them to z's. Whoops, forgot these two. There. So this is the z extents. X, y, and z extents. And now we also need to say func f floor neighbors neighbor count. And it returns an int. Oh, neighbor count, but it has to take a hex tile. For underscore offset range chords. So we're going to go once for each coordinate. We're going to ask how many neighbors you have. Immediately adjacent. We don't look at ourselves. We only look at adjacent tiles. So for adjacent tiles, we are going to say it's a weird rule, but okay. So we have X tile, and we say, and we have an add function which modifies the tile. So So this has to be colon equals there, and now we have to return count. So now we can count the number of neighbors for a given tile coordinate, and day24b says I'm going to run a generation on each floor. Oops. So we need floor generation. Func f floor generation, which returns a floor, and we say new floor is make floor for x in the range of, oh, you know what? I'm going to, instead of x extends, I'm just going to I'm going to return and I didn't even need z reextends because I can calculate z from x and y. So what I want to do is get I need the full range of viable coordinates. Is it possible? So let's just imagine if we had a line of horizontal cells, that would be z equal to it's a whole bunch along the z-axis, but the x and y-axis, their extents are both 0. So if I just iterated over x and y, then I wouldn't be finding all of my cells. This is interesting. How do I enumerate cells that are in the map here? Okay. If we the point is that we can't be looking at all combinations of x, y, and z, because all combinations of x, y, and z aren't valid coordinates. What we need to be looking at is well, we could generate the list of possibilities as all neighbors of all existing cells in the map. And that can look exactly like a floor. It's just a floor where we essentially populate all the, we say we're going to add everybody to that map that could be affected by this. And then we're going to go through and eliminate them based on whether they should have been there based on the population of the source map that generated it. So instead of our extents functions, I'm not going to delete them yet, but I'm probably not going to use them because they don't really help us. We're going to create a new floor for tile in F, range of F. We're going to write a neighbors function, which just returns a slice of neighbors. I'll just use append. Not counting, I'm just neighbors equals append neighbors. Oh wait, I'm going to undo that. because I do need to do that. Need to add the offset, and now instead of counting them, pen neighbors t. And then we're going to return neighbors. And then for counting neighbors, neighbor count isn't a floor. That's really a function on a hex tile, because I don't use the floor at all. So I'm going to change this to H, hex tile, and okay, that's pretty good. So now we have neighbors, neighbor count. We're going to make a range new floor. Actually, we need a, let's do possibilities. Well, we're going to need new floors, and we're also going to need a possibilities list. So wait a minute. We have a set for every tile that's in the list. We can count its neighbors in the existing list. Every time one of the neighbor tiles, we can count them, whether it's in the existing list, and possibly add it to the target. So we don't actually need to keep a separate thing of possibilities. We can just do for neighbor range tile dot neighbors. So we ask for every one of the neighbors all the tiles we need to consider also include the tile itself. So we're going to also consider, so if tile dot neighbor count, so we know that the tiles that we are considering are guaranteed to exist because they have to be black. So any black tile with 0 neighbors or more than 2 neighbors dies, flips to white. So if tile dot neighbor count, if floor dot neighbor count tile if n equals 0 or n equals is greater than 2, we are going to, no, well actually, so if n equals 1 or n equals 2, we're going to add it to the next grid. Otherwise, we're not going to add it to the next grid because it's going to die. So, new floor, tile dot hash equal tile. Great, so that controls whether the tile we're looking at is in the next world. Now we need to look at all of its neighbors because all of its neighbors are candidates for possibly becoming tiles in the next world as well. So now we ask for its neighbors and we basically do a neighbor count in the floor of those neighbors. So we're going to calculate this again. Now, by the first thing here, we know that our tile is black. And we know we're going to hit every one of them by this loop. In the neighbors, if the tile in the world is black, we have to worry about the black rules, but we're going to get that automatically. So here, we only have to look at tiles that are in our neighborhood that are white, and then we can follow the rule for what happens with white tiles. So, instead of doing we'll just do this. Here we go. So we're looking at the neighbors. Actually, we want this to say, does the tile exist in the floor? And if it does, we can ignore it. Only if it doesn't do we say, okay, how many neighbors does that tile have? And now we have to say, if n is 2, then we're going to add it to the floor as well. And since we don't use this anywhere else, I'm going to put this in here. Oh, and here we don't say tile dot hash, we say neighbor. All right, that runs a single generation, and then when we are done, return the new floor. I feel like that's pretty close. So this takes generations. And, oh, I got generations is an int. And now day 24b So what happens when we run this for 2208? Is that the number? 2208. So we can take and change this to input.text. I love it when a plan comes together. 3802. Now it'd be kind of fun to write a visualization of this cellular automaton. And that is the right answer. It would be fun to write this visualization just to see I've never seen a cellular automaton running on a hex grid. Seems like it would be a fun thing to explore. So maybe someday I'll do that. But for now, we've done it. We've solved day 24. And hopefully tomorrow I will get around to doing day 25. So hope you all have a great day. And thank you for watching. As a reminder, you can, give me a follow on this. Once this project ends, then I'm going to start working on some interesting stuff that I hope people will like. I'm going to be working on a cool hardware and software project, and kind of streaming the construction process. So hopefully people will enjoy that as well. And playing with some sort of light hardware device, possibly Raspberry Pi, possibly Arduino. I haven't decided yet because there's a lot of interesting design criteria to mess with. So keep an eye on here. Click the follow button. I'm also on YouTube as Kent Quirk. I'm on Twitter as Kent Quirk, and I always announce on Twitter what I'm going to do. These Twitch streams get reflected to YouTube, but I may switch to YouTube Live. We'll see. So hope you all have a good day, and I'll see you next time.